Now we will define the unitary and ladder operator. What is unitary operator and what is ladder operator? To define the unitary operator, an operator A is unitary operator if this condition is satisfied. The condition is A inverse operator is equal to dagger. Okay, inverse of operator A is equal to dagger of operator A. Okay, such that operator A and its inverse should be equal to inverse of operator A and the operator A. This is equal to 1. Okay, so this is the definition of unitary operator. Now we will define the ladder operator. What is ladder operator? These operators are used to step up or step down. Means ladder operators are used for what purpose? First of all, we are defining the characteristic of ladder operator. These operators are used to step up and step down, raise or lower the eigenvalue corresponding to certain arbitrary function. An application of these operators in field theory is the use of creation and annihilation operators, usually symbolized by, okay, these operators are usually symbolized by, ladder operators are symbolized just like as dagger. This is dagger and A. Okay, ladder operators respectively, where A operator dagger makes creation. It makes creation and this means it makes annihilation. So these operators are used in a certain term. The term is annihilation, used in quantum physics. It is a complete article. What does it mean by annihilations? Where the microparticles, just like photon, we discuss the motion of the light particle just like photons and its mass and momentum and its probability for striking, just like that. Okay, so these operators are used in the article of annihilations, ladder operators. And when we multiply, just like as operator and dagger with operator A, then what does it mean by this? Usually counts the states. It count the state, count the states. Okay, and is known as number operator and known as number operators. Okay, these operators are dimensionless. There is no dimension of these operators. Okay, the second thing is these operators are dimensionless. Okay, they are applicable specifically for the system whose Hamiltonian can be expressed as, okay, these operators are used for what type of system? The system whose Hamiltonian can be expressed as, where Hamiltonian dagger and this and or we can write and for Hamiltonian, okay, Hamiltonian is represented by H usually. The use of these operators makes the result independent of the specific dynamical variables of the original problem, therefore reducing very complicated problems into simple algebraic equations. So ladder operator is actually used for some sort of purpose. It is used in annihilation, it is used as Hamiltonian. Okay, and there are certain types of, just like as, okay, these are the certain types of operators, and when we multiply these operators, then it means that these are used to count the states and known as number operators. Their multiplication is known as number operators, and these operators are dimensionless. Okay, and as I have already explained that these operators are used where Hamiltonian is produced. Now we are going to prove a theorem. The statement of the theorem is, if two operators possess common eigenfunctions, then they commute. Okay, let me start the proof of this theorem, and first of all we will look on the statement, what is given in the statement and what we want to prove. The given is there are two operators and the two operators possess the common eigenfunctions. We want to prove that they commute. Okay, so let psi be the common eigenfunction. Let psi be the common eigenfunction of two operators A and B. The eigenvalue equations are when operator A is applied on eigenfunction psi, then we get A psi, and let this is 1. And similarly, when we apply B on psi, then we get B psi, and let this equation is 2. Okay, operating 1, operating equation 1 with operator B, we have, okay, so when we operate B in 1 into A psi, which is equal to B into A psi, and this will be just like as BA psi is equal to A into B psi. A, and when we apply the operator B on psi, it will be B psi. Okay, so let this is 3. Now operating operating 2 with operator A, then we have, okay, now we are operating 2 with operator A. 2 means equation 2, so this will be just like as operator A is apply on B psi, and this will be equal to operator A and B psi. So this will be operator A and operator B psi is equal to B into A operator psi, and this will be equal to B, yes, B into A psi, or this can be written as AB into psi. So let this is 4. Okay, now from 3 and 4, now from equation 3 and equation 4, we have AB is equal to BA. This can be written as operator A, B, B and is equal to 0, and this can be written A and is equal to 0. So we have proved, okay, converse is also true. It's is also true. Hence, if two operators possess common eigenfunctions, then they compute. Hence, if two operators possess common eigenfunction, then commute. In this lecture, we are going to discuss about harmonic oscillator. To describe about harmonic oscillator, we are taking a particle, and the particle is moving under a potential barrier defined by Hooke's law. Okay, so a particle moving under a potential barrier. Defined by Hooke's law is defined as harmonic oscillator. Okay, a body moving under simple harmonic motion simple harmonic motion can be represented by sine or cosine. Cosine wave. With x is equal to r cos omega t or x is equal to r cos theta. Where r is amplitude, okay. Hooke's law is, when we talk about Hooke's law, then it is f is equal to minus kx. Okay, so when we talk about velocity, the velocity is v is equal to dx over dt, and this is equal to minus r omega sine omega t. Okay, and the acceleration is, it is dv over dt. Okay, this will be equal to minus r omega square, okay, cos omega t. And this can be written as minus omega square and r cos omega t, and this will be equal to minus omega square, and this is x. Okay, so we can write f is equal to minus m omega square and x. The negative gradient of the potential is called force. So force is equal to minus dB over this is V potential dx. Okay, so this can be written m omega square, okay, and x is equal to dV over dx. And if we integrate from 0 to x, and this is dV over dx with respect to dx, m omega square and x with respect to dx. dV is equal to x and 0 to x, and this is from 0 to x, which is equal to m omega square. The integral of x is x square divided by 2, and this is from 0 to x. And how to apply the integral? Upper integral minus lower integral. Okay, so this is v minus 0 and m omega square, this is x square divided by 2 minus 0. So this will be v is equal to 1 over 2 m omega square and x square. Let we name it, this is equation A. Okay, oscillator, the potential energy function for equation A. The potential energy, yes, potential energy function for harmonic oscillator or harmonic oscillator is given by, and this is kinetic energy, which is equal to 1 over 2 mv square, and this can be written as 1 over 2m, means we are multiplying and dividing by m. It will take the form m square and v square, so this will be equal to, it is actually p square. This is m square, v square is momentum, p square over 2m. This is equal to momentum. And when we talk about the total energy, which is E, the total energy which is E of harmonic oscillator, at any instant, is therefore this is E is equal to px square divided by, now we are talking about total energy, okay, so 1 over 2, and this is m omega square and x square, okay. The classical expression of total energy of harmonic oscillator, yes, this is, you can say, classical the total energy. So we have written this total energy, and when we talk about the classical expression of total energy, so let this is A, no, when we talk about the classical expression of total energy, the classical expression of total energy of harmonic oscillator is given by it. And this is E is equal to px square divided by 2m plus 1 over 2 m omega square, and let this is equation 2, okay. The quantum mechanical operator of total energy E of a system is known as Hamiltonian. the quantum, now we are talking about quantum, the quantum mechanical operator. Quantum mechanical operator of total energy E of a system is known as Hamiltonian. Okay, Hamiltonian, and this is represented by Hamiltonian represented by H. Therefore, the quantum mechanical expression for energy of harmonic oscillator therefore the quantum mechanical expression for energy of harmonic oscillator is so above equation 2 will be equal to harmonic oscillator Hamiltonian. Okay, when we talk about the above equation in quantum mechanical operator, then it will become Hamiltonian. So it will be equal to Hamiltonian, which is px square divided by 2m plus 1 over 2 m omega square and x square. Okay, let this is 2, or this equation is actually 1. Okay, we define two dimensionless operators, and after defining those two dimensionless operators, we will prove the result. Okay, what we are proving over here, A and dagger operator A and its dagger, this is equal to 1, and we name it equation 3. Okay, these are two dimensionless operators, dagger of operator A and operator A for harmonic oscillator, such that their commutators should be equal to 1. Okay, These are harmonic oscillator. These are operators. These tools are operators for harmonic oscillator, and we want to prove that their commutator is 1. So when we talk about A, where the value of A, what is the value of operator A? It is 1 over 2m omega h cut, and its square root. Okay, inside the parenthesis it is iota px operator plus m omega x operator, and let this equation is 4. Also, when we talk about dagger operator, okay, it will be just like as it is 1 over 2m omega and h cut. Okay, let we see the difference. Where is the difference? The difference is only we get over here the minus sign, px plus m omega and x operator. Let this equation is equation 5. Okay, now when we put these equation 4 and equation 5, the value from equation 4 and equation 5 in equation 3, then it will take the form just like as. Our calculation is a little lengthy over here, but you don't need to worry that the calculation is lengthy. Okay, we will try to make it simple. So we have just to put the value of A and operator A and dagger of operator A. Okay, so first I am putting the value, the first value, which is 1 over 2 m omega h cut iota px plus m omega and x. Okay, and 1 over 2m omega h cut. Okay, and this is minus iota px plus m omega x. So after putting value, we have put the equation 4 and 5 in equation 3, and you can see over here that we can take the common 1 over 2m omega h cut. One thing I would like to describe over here, that might be you will think that from where we have picked the value of equation 4 and 5, how we know that the value of A is operator A is equation 4 and the value of operator dagger of operator A is equation 5. Yes, there should be question in your mind from where these values we have picked. Actually these values are already defined. Okay, so these values and these value have proof. Okay, so we are not going to the proof of operator A and its dagger. We are directly using over here. It's okay. So this is yes, it's square. Okay, and inside commutators we will write iota px, okay, plus m omega x comma minus iota px plus m omega but before expanding this we are using what we are using we are using this result, which is we have already defined the properties of commutator, which is operator a plus b operator comma c operator plus d operator. This is actually equal to a and c and plus a and d operator plus b and c operator plus b and dear student, maybe you are experiencing the background noise, so I am sorry for that. Actually I am living in a noisy area and this time I am picking that time where there is less noise. So please, if you feel that there is background noise, neglect it. So I am explaining each and everything very slowly. It is because we are studying about quantum physics and these operators and notations are a little bit hard to understand. So that's why I am moving very slowly. So if we will move slowly, then these operators, these notations are easy to understand. So now we are using this, using this result, we will open this commutator. Okay. So when we will open this commutator, we will get just like as this will be equal to 1 over 2 m omega and h cut. Okay, so this is iota px and minus iota px. This is first plus iota px and m omega h cut plus m omega x operator and comma minus iota px. And last is plus, it is m omega and x comma m omega x. Okay, so now we are going to move to the next. Is equal to 1 over 2m omega and h cut minus iota square px plus iota m omega. And it is x minus iota m omega x and px plus m square omega square. Okay, and this is now we are using just like as we know that x commutator of x and x, these two operator is 0. Okay, also when there is a constant just like as a into x operator, this will also equal to 0 where a is constant. Okay, so 2m omega and h cut, this is equal to iota m omega, and here we will only have px and x, this will be 0. Okay, so we get only save this and this, it is also 0. Okay, so this is minus iota m omega
x px, and we will close the square bracket. Now this is equal to 1 over 2 m omega h cut. Okay, 2 m omega h cut, and we are writing over here minus iota m omega. Why we are writing minus? Because we are changing the position of x and px. We will write first x then px. Okay, due to that we have write over here minus. So why we have do this? Because in the second commutator we want to make the similar commutator. So minus iota m omega, it is also x and px, and these two x and px will convert into 2 times. Close the parenthesis, square bracket, and this will be equal to yes, this will be equal to this is 1 over 2 time of, means we are adding these two, minus 2 time of iota m omega over 2m omega h cut, and this is x and px. X and px. The value of x and px will be equal to minus 2 iota m omega over 2m omega. Yes, h cut, and this will be equal to the value of x comma px is minus, it is actually minus iota h cut, and we have minus iota square after cancellation. This will be equal to 1. So this was the result that we want to prove.